哇，数据清洗分析方法开始。哇，这好激动哎，这有点太激动了，我觉得。OK，我好开心，真的非常期待，又在这个时间跟你们一起上课。Let's do it. So today, I am really excited and really looking forward to a class that I think is very important, and that is data cleaning and picking and using communicating analytical techniques. And so let me give you two things and then context. The two things are what this is and what this isn't for this week. So let's talk about what this is. So what we're going to do today, and we're going to focus on in this lesson, is to understand how you prioritize data, how you pick an analytical method that works, and how you communicate the analytical method so that other people are excited about your results, are excited about the implications, and take action, make business results. So that's the goal for today. It's to power and to equip you to use analytical techniques to have an impact in the organizations you're going to be a part of. So what is this not? What this isn't is a look at all of the analytical techniques that exist. We're not going to deep dive into neural nets. We're not going to look at principal components analysis, though we could. And there are two reasons why we're not going to do that. The first reason is that there are plenty of great places for you to do that in other places. So you could go online. There's great resources to understand how communication works, how you can understand how neural nets work, how principal component analysis works, all these technical things. You have resources online, and I'm happy to talk about them during our live one-on-one or with the group. So I don't want to dive into that. The other reason is that regardless of the analytical technique that you end up using, if you can't communicate it well, if you can't show why it matters or why it's important, it doesn't matter. And here's the context. So you will likely, after this course, be hired by a great company that's excited about your skills, excited about your ability to deliver on results, and that's going to make you a really effective employee. But if you want to move up and you want to become a manager, become a VP, become a chief data officer, what you need to understand is not just how to implement analytical techniques, but also how to choose between analytical techniques and communicating that. How do you know, given a business problem, what analytical methods you're going to use and what the implications of those methods are going to be, and how can you explain them to your colleagues, to your boss, whom probably don't know how to use them in a way that they're excited about and they're convinced. So that's the goal, and that's the context. In order to move up, you need to understand how to choose between methods and do so effectively. So I'm really excited for what we're going to dive in. So let's dive in and get into what the nitty-gritty is that you're going to learn. So let's move from here. So we are going to be focusing on 4 things over the course of this session. First, we're going to start off with data cleaning and prioritization. And this is a natural extension from last week in our last episode. Previously, we talked about how do you understand what data has? How do you understand what's in the data and what's happening within it? Once you've done that, and once you've deep dived and you've seen, oh, this is how the data is structured, these are the different parts, etc., you're going to realize, oh man, this data is probably dirty. I need to do something with this data. You can't spend all your time on it. Like the example we gave previously, you can't spend 2 months trying to clean all the data. So how do you prioritize? Next, we're going to look at different analytical techniques and how you trade off between them. When is a linear regression good? When is a random forest good? When is a unsupervised learning technique good? We're going to talk about that. We're then going to deep dive into linear regression. And the reason we're looking at linear regression, which many of you guys have likely already studied, is because of that reason. We want to use a method that is widely applicable, people use it all the time, that is understandable, that has business implications. But most importantly, because we want to give you a template for how to think about analytical techniques. So we're going to use a more simple method like a linear regression, and we're going to push you to use that framework to explain more advanced things. So if you're explaining what XGBoost is, if you're explaining what a analytical method that you made up is, you're going to need to have the exact same skills. And so we're starting with linear regression because it is the most important technique that you can have in your toolkit right now. Finally, we're going to work on just that. How do you communicate about an analytical technique? How do you get people excited about what it's going to be? So these are our goals, and it's going to be a really wild and fun ride. There are 3 main categories, again, data cleaning, analytical techniques, technical communication. I'll let you guys dive into these at the end. Do you feel like you learned it? Do you feel like you understand it? If not, go back to the video, bring up questions for the one-on-one, talk to your TA. I want to go into what the homework is. So what is the homework for today? And if those look scary, good. It should, but it should also feel quite manageable by the end of this. The first thing you're going to do is you're going to work on a data cleaning worksheet, and this is to practice the skill of prioritization. You're going to learn a framework called SIR, which helps you understand which data matters and which data doesn't. So that's going to be your first step. The next is you're going to implement a multiple linear regression, which you will be doing likely in R, though you can use another language if you prefer. And you're going to do that both for the Japanese and US data set. This is all the same video game data set as before. Finally, you're going to develop 3 pages that explain what are your results, what are the implications for the business, and why did you choose linear regression? What is linear regression? Imagine you're writing this for someone who's never done anything in statistics, data science, a data analyst, whatever. And then finally, there's some additional readings for you to choose from. But if this seems daunting or if this seems easy, I think for those who this seems scary, we're going to walk you through how to do this so that you can get out of it and rock your assignment. And for those that this feels easy, great, you're on a great track. Focus in on the communication. How do you take your understanding and move it to the next level so that you excite your manager, so that you excite your colleagues, so that people say, wow, this person is not only really technically smart, but they also understand how businesses work. We have to get them in a leadership position here. So that's what we're going to focus on today. This is the homework sheet that you guys will be working on. So I think it will make a little more sense when you are doing it, but this is you'll be using the SIR framework in order to build this out. So this should motivate what you're learning. This should motivate how you are thinking about this upcoming session, but it's a really, really exciting one. So let's do it. And now I'm going to pause right here, and then we're going to move, pause right here to let you look briefly over the homework, understand it, and then I'm going to dive into data. So let's talk about data cleaning like I just introduced. And I know we have a variety of backgrounds here in this class, and that's why I'm really excited about this, because if you are a data scientist or data analyst, or you want to get into that field, you have to realize that a significant portion of your time, some people say 60 to 80% of time of an analyst, is just spent cleaning data. And I think that's accurate, if not more. If you are coming from the management side and you want to be able to have a conversation with someone who's focused on data science, with a technical team, then you need to realize how much time it's going to take for them to clean something up and to make the data presentable. So you can ask for something, but in order for your ask to be reasonable, you really need to understand how data cleaning can be such a significant part of our work. So let's talk about why we clean data. And I'm going to use an example that we will use quite a bit over the course of this session. And this example comes from me from a specific industry use case that I had a couple of years ago with a retailer. So a retailer came to my team and said, hey, we are interested in finding out the most productive pieces of clothing that we have in our stores. So could you help us out with that? And we have some data, but we've never figured this out. We've never been able to get at such a granular level. Could you help out with that? So not a too difficult analytical question, but you have to be a little bit more specific. Like we talked about in our live session, the best practice for someone that's working with analytical teams is to be very explicit about what it is that you're asking. So what does productivity mean in this case? In this case, what productivity means, we're looking at store level productivity. It actually refers to two things. One is how many items are selling. So it's the sales rate. But two is how many items are currently available in your inventory. So if you imagine you have one item that sells one a month, another item that sells one a month, but item A has only one piece of inventory and item B has 10 pieces of inventory, item A is much more productive than item B. So that's store productivity. It's when you think about how quickly, when you have something in your inventory, how quickly it goes out. And that's a good measure for how much money you're making off of every piece of clothing that you're using. So that's something that's used in the industry. It's called inventory turn. And it's a good metric for how productive you're clothing. So they came and they said, we want to understand what is the most productive piece of clothing that we have in our line. And so I came to them and I worked on the data, and I made a early mistake because I thought I'd cleaned the data, but I'd actually missed an important part. So I merged the data together because we had sales data and inventory data separate. I came together and then I showed them and I said, hey, it looks like your most productive data is, your most productive piece of clothing is these yellow shorts. And I got these yellow shorts. I was like, oh, these are the best shorts. You should really use them. And you should really promote them. And the client team kind of looked at me, the retailer, and like, these are definitely not our most productive. These are ugly yellow shorts. Why would these be most productive? He said, you should really go back. I think something's wrong with your data. And so I went back, and let me explain to you what happened and why effective data cleaning would have solved this problem, would have made me look better in front of my team, and would have gotten us to the right answer, even though I got to the wrong answer. So here's what was happening. So we have two pants. We have sales data and we have inventory data. And we have to figure out, and in order to merge these two data sets, we need to use these three unique identifiers. And let's pretend in this case there are only three. There's color, there's fit, and there's size. And if you have these three, then you have a unique pants. So they're looking to say, okay, what is our most productive pant size combination? So we need these three characteristics. So if you look at these two pants, you look at the pictures. These are, by the way, not at all the pictures of the actual company. I'm just using this as an example. I don't even know where these pants are from. They look nice though. They're good pants. Should I get those pants? Okay, never mind. So let's look at these two pants. If you just look at them, honestly, they probably look quite similar. Just from a visual inspection, they look like they're pretty much the same. And let's go down the line. So we have color, brown, same on both of them. Fit, baggy, same for both of them. Size. So if you don't know much about pants, and sorry this has become a lesson on pants, but I think pants are awesome. For men's pants, and for at least in the US, I think this is true in China as well, there are two sizes to look at. The first is the width, how wide it is. This is in inches. The second is the length. So this is 32 inches, 30 length. It's a very normal size for men in the US. So you look at these two and you would say, okay, well, on the left side, it's 32x30. That probably means 32 width, 30 length. Perfect. And on the right side, you have 32W width and 30 length. Perfect. So you would say, okay, these are, I figured it out. I'm a genius. Let's go. These are the same pants. Answer over. But what happens when you merge the two data sets using R and using SQL? In this case, we use SQL. SQL isn't smart enough to know, well, 32x30 is pretty much the same as 32w30. Instead, it combines these three strings, brown, baggy, 32x30, brown, baggy, 32w, 30l, and it looks at them and it says, oh, wait, 32x30 is not equal to 32w, 30l. So we have no data on the productivity. So I said, okay, well, I looked at the data, I merged the two, I thought I merged it well, and I ended up not merging these data sets at all. So these are the most productive pants, but when I looked at my own data, it said they had sold nothing. Now, this is a great example of how data cleaning would have solved and would have gotten me to the right answer, or in my case, I didn't do enough data cleaning, I didn't work hard enough, I didn't realize what was the problem, it got me to the wrong answer. And oftentimes, it's not just that you clean the data and it's done. You actually have to make decisions about how you want to clean the data and how much time you want to put into it. So imagine you're me, you just came back from this meeting with executives and you are scared shitless because and that just means that you're scared because you messed up. And you're trying to figure out, frick, how do I fix this? I don't know how to fix this. So you're going to go back and you say, okay, you look through the size, like, oh, this is the problem, size is the problem. How can I fix this? And you think of two options to fix it. One option is going to go through every single thing and get it exactly right. So you're going to and we don't need to get too technical here, but you're going to figure out what you're going to see whenever you see a W, you might remove it. Whenever you see an L, you might remove it. And then you're going to separate these two apart. You're going to have a width, which will just be the 32, and a length column, which is the length column, which will just be 30. And you're going to do that for both of the two. You're going to clean up both sides of the data. And this is a better approach, but it's going to take a while because you have to make new columns. You have to be exactly precise. You have to use a regex format, which just means that you have to parse through the data. So option one, long, it's going to take an hour and a half, but clean. It'll clean most variants of the data. And then I thought of option two. So what is option two? Option two is, I'll teach you guys an English word. It's called a janky solution. And janky just means that it is not a very well structured solution, but it gets the job done. So this will take me 30 minutes. And all I'm going to do is I realize, oh, okay, the right hand side had, the pattern was, let's look at this pattern right here. Number, space, space, number, space. So the first two are the number, and the second and third to last are another number. Let's pull these two out, slap an X in between, and then it'll be the same as this. So this is actually a faster method. It wouldn't take that long, and you would get the right answer for these pants. But there's a problem. And the problem is that you don't know if this is actually going to work for all the variations. So what if you have a size that is not two numbers? What if it's 8W space 30L. In this case, you would extract the 8W x 30, and that would be wrong because this side would just be 8x30. So this solution is fast. The second solution is fast, but it's not perfect. And before you jump to a conclusion and say, well, obviously you should pick the clean one, why would you pick a bad solution? This is an example that will follow time after time after time when you've touched data. And when you're working with data scientists and analysts, you will always come down to this tension of how much effort should I put in to clean my data versus how quickly do I need it clean. Let me say that again. How much time do I need to put in to clean my data? How much effort versus how much time do I need to put in? So effort versus time. Do I go fast and dirty, or do I go quick and clean? Or slow and clean? If you go quick and clean, I'm impressed. Touche, good sir. So let's figure out, how do you make that trade-off? And in this time, I went back to a framework called the SIR framework. So when you're thinking of the trade-off between doing things right or doing things quickly, think of three main things. The first is the size. So does this cleaning affect a large group of the data? So are you cleaning one column? Are you cleaning 20 columns? Imagine I have different types of sizes for size in US, size in Europe, size in Asia. Each of these are slightly different, but my method will apply to all of them. Does it affect a big chunk of the data? Another way to think about size is if the only problem was this pair of pants and nothing else mattered, or nothing else was affected, then I could probably go for a very fast and dirty solution because it only affected these pants. But if it affected all of the pants, then maybe I need a cleaner and more accurate solution. So that is size. Let's talk about importance. Importance is, how much do I need this data to be right? In this case, if I don't have this data right, I cannot do the analysis at all. So I can't merge these two data sets. So in this case, it's quite important. Now, you might say there could be other analyses which are more important, and if they are, then prioritize them. But in this case, in order to do the analysis, I have to get this done. So it's very important. Imagine that size is actually not necessary. So the client's not interested, this retailer is not interested in size. They're just interested in the fit and color. So in this case, it was brown and baggy. And they don't care which sizes are affected. Just put all the sizes together. In that case, size doesn't really matter. And you could probably clean it up more quickly, or you could decide not to clean it up at all. Finally, SIR, repeatable. What repeatable means is, how many times are you going to do this analysis or this cleaning? Similar to size, you might find that in order to clean this piece of data, you're going to have another data set that has a very similar problem. And if it is similar, you're going to have to use the same type of code or strategy to clean it. Then think about using a more clean but long method, because you'll actually be saving yourself time in the future. If you go back, imagine this size problem happens in every single data set that you're going to come into, with slight variations. Like I gave you the like the exception, which was 8W30L right here. If you're going to face stuff like this in all of your data sets, then you want to spend more time on it. So that is repeatable. And if a piece of cleaning is repeatable, then you should consider spending more time on it. So let's talk about how you prioritize cleaning, and then we're going to do a quick worksheet on it. So this is called the agile approach to cleaning data. And I want to be clear that in order to be effective, a successful data analyst, it is not just knowing about fancy analytical techniques. In fact, that is just a nice thing to have. It is about being able to move and get insights from data quickly and effectively. And in order to do that, you need to move. And if data cleaning is 60 to 80% of your work, then if you can make this faster, then you're making yourself a 50%, 100% better of a data analyst. So the method that I use, and what I would suggest using for you, is called the agile approach to cleaning data, which is a very big word for saying clean what you need to and nothing else. So I gave you guys the example in the last session where someone spent 2 months trying to collect all of the data that they needed. Wow, they went rounds, they got, this is for an e-commerce data set they want. They got store data, they got customer data, they got product data, they got every single piece of data they could ever need. And they combined it, and they did this amazing analysis that showed the only thing that mattered was customer data. So how could that have been avoided? How could they have saved us 2 months? And they could have focused on just getting what mattered and focused on what mattered first. So similarly, the same applies to data cleaning. You could spend your entire day cleaning all sorts of data, but you only need to clean the data which is going to be most relevant for your analysis. So I'll get, in the previous example, I could have cleaned size, and in that same data set, there was also a problem with the stretch variable. How stretchy are your pants, for example? Did I clean it? No, because it wasn't a part of my immediate needs. So you might be tempted to go through your data, try to clean everything you can, but don't get trapped in that, because you want to be able to move as quickly as possible so that you can make quick insights and quick decisions using the data. So the 3 steps are: go through exploratory data analysis, then clean the data. The EDA shows you what's weird with my data. Cleaning helps move it on, and then you can do an analysis. And the analysis is going to lead you to say, oh, I actually need this new data source, or that's weird, like in my case, this doesn't seem right, let's go back. Let's figure out what it is. So then you go back into the exploratory data analysis and say, okay, what's happening in my data? That's the agile approach to data cleaning. So here's a little bit of a practice for you guys. And the question is, should you clean this data? I'm going to go quickly over these, and I want you guys to spend 2-3 minutes on, pause the video, look through this, see if you can figure out what does or does not need to be cleaned. So we have sales data. Those are the context. The context is that you are in a company, an online e-commerce company that is trying to predict sales for pants. A little different than my example, but similar, trying to predict sales for pants. And you have some data sources which you would like. So one is sales itself. The next is size of the pants. The next is color. We have fit, which is the type of pants. Is it slim? Is it baggy? Is it wide? What type of pants are they? And then we have store location. So let's use the SIR framework, which we'll see is how large is the data, how important is the data for the analyses, and then is it repeatable? I'm going to give you guys 3 minutes to go through and try to prioritize going through these. I want you to do 2 things. I want you to say, 1, should you clean it at all? And 2, which you would clean first, second, third, fourth, fifth, if you had to clean them all. Okay, I'll give you guys a second to do that, and we'll come back together. So what did you think was the most important? there's definitely you can be open to debate about what is somewhere in the middle. But I think that without a doubt, the most important thing that you could work on in order to predict sales is the variable sales. So I probably would have focused on that first, because you can always, in an agile way, get sales clean, and then move on, make some predictions, come back, clean some more, make some new predictions, come back, clean more. And that's actually often how projects work, that you are simultaneously cleaning the data, making new predictions, and then you're saying, this is good, but let's make it even better. I want to add in this new data source. And that means that you're going to go back and use another data source, which means, like we discussed in this circular process, you'll start cleaning data again. So I'd probably say it's most important. Next, it's difficult, and we can talk about this during the next session. I would probably say size is the next most important. You have to have it in order to join on the data. So in order to know how productive something is, you need to be able to join on that. And if it's not perfectly clean, then you won't be able to know a part of your data's or maybe a significant chunk of your data's productivity. So I would rank that very highly, definitely would clean. Then I think there's probably a tie between color and fit. I might give it to color because there's some repeatable element. So if I'm going to spend some more time on this, it might help me out more in the future. And then finally, for store location, I might not even clean it at all. Another layer to this is how much time should you spend cleaning it? And it's actually a little bit less clear. For sales, if you're going to never use it again, you could probably do something that's quick and dirty if you never have to do this again, as long as it works. With size, it's something you're going to reuse. So I would spend more time figuring out the right way as opposed to a clean way. And then color and fit are probably a mix of those two. So always think about that. It's not just about whether or not I should, but it's also how rigorous do I need to be when I'm making these variables clean. So I'm really excited. We're going to dive now into trade-offs between analytical techniques. And so this is going to get you into the conversations, especially if you come from a not very technical background, of when you're talking with other technical data scientists, data analysts, and they're saying, I'm wondering what analytical approach we should use. This is the perfect opportunity for you to now get a little bit of experience into a broad range of analytical techniques, and then have a good framework for thinking about what is and isn't most useful. And I'm going to use two main frameworks to think about it. One is a 2x2 box, unsupervised, supervised, continuous, not continuous, and another is interpretability versus accuracy. So let's go through that. First, like with all of our problems, we want to start with a real business problem to ground this, to make this effective. So here's the problem. And this is the problem that we are going to explore for the next 2 weeks. This is the problem that we have been exploring in last week. So how can we predict the income of a job given the characteristics of a job? And what are the characteristics of a high-paying job? So this looks like if we think about it, what are we trying to figure out? We're trying to figure out a prediction. So we're trying to say, okay, this job is going to be high-paying. That's a prediction. The second is we're trying to figure out what are the characteristics. So what leads us to believe that it's high-paying? That's about figuring out the underlying factors that lead to this. And then the final one, which might not be intuitive, is how we're predicting. And there's actually two choices here. One is, are we predicting the salary, which would be continuous prediction, or are we predicting whether or not it's high paying? And that might be decided based upon whether or not it's more or less than, for example, $4,000 or $5,000, for example, per year. This is an example. So let's go through a really famous and useful framework for thinking about the types of analytical techniques that are used. And it's, working at McKinsey, we always love 4x4s, and I think this one's actually quite useful. So there's really two main dimensions that algorithms go on. And in our live, we talked about a third dimension, which is the amount of data needed. But let's focus on these two for now. And the first one is supervised versus unsupervised. Supervised means that you know what the answer is. You have truth. For example of this might be you're predicting income for another job, but you already have data which is predicted, which gives you the income of previous jobs. So if I have data for a lawyer, data for a doctor, data for a policeman, a fireman, a government official, and I'm trying to predict the income for a elementary school teacher, I can use the data I already have to predict this. That's supervised learning. Unsupervised is we don't have an answer. We're trying to figure out something about the data, some structure. Often this means that you're trying to understand groups. So this might be clustering, dimensionality reduction. We'll talk there. The other two are the types of data being used and the types of prediction being made if it is predictive. The first is continuous. Continuous is that there is no set of categories. So an example of this would be income. You can make $400, you can make $527, you can make $21,000. It's continuous. Categorical is either binary, high, low, yes, no, A, B, or multiple. So for example, you could say, I think you are most likely, given data, I think you're most likely to be a fireman, policeman, or nurse. Given the data, I predict you to be a fireman. That would be categorical. But those are all categorical examples. To talk about some of these specific examples, I think, frankly, supervised learning is a little bit more used than unsupervised. Unsupervised is useful, and I've used it before. Supervised learning, let's give some examples of supervised learning algorithms. You've probably heard of these. It's good to think about them. We have linear regression, or just some different types of regression, polynomial, linear, which we're going to discuss today. We have decision trees. Those are these binary trees which say if you're more or less than X, you choose this. If you're less than X, you choose this. That's a decision tree. You have random forest, and these are random forest actually could be continuous or categorical, could be used for either. But it's a little bit more of an advanced tree-based method. And so if you're doing supervised continuous learning, you might be predicting sales, forecasting demand, you might be finding drivers of store performance. So that's what you're doing here. Right over here we have categorical types of supervised learning. This is where we're trying to predict A, B. The most famous is the logistic regression. This just predicts it's a binary 0, 1. But then we also have others. We have trees. Trees appear in both. Random forest actually is in both. Support vector machine is often used for categorization, but it could also be used for continuous. So you see there's some overlap between these two. This is if you're trying to decide, a really famous example is predicting churn, customer churn. Will or will not a customer continue to work with or serve or be a customer of your company? That's churn, and that's a useful thing. Another target thing, for example, we talked about using genes to predict whether or not you have a candidate gene for cancer, for example. This would also be potentially a supervised categorical problem, and you might use something like deep learning, which would also could also fall under here. Though again, deep learning could fall in either of these two. What is unsupervised learning? So unsupervised learning, as we talked about, has a couple different examples. This is when you're trying to break things into groups, or you're trying to reduce the amount of variables so you can visualize something. So k-means is a really famous way of grouping. It allows you to group different customers, for example, different products together into, let's say you have 1,000 customers and you want to say, how should I target them? It's a lot of work to target 1,000 customers all individually, especially if you're a traditional company. A easier way to do it might be through segmentation. So you say, okay, I think there are 3 main groups, and use segmentation. You say, oh, I found out these groups are the old, middle-aged, and young, for example. That is unsupervised continuous learning. And finally, unsupervised categorical learning. This happens a little bit less. You're essentially trying to break, but conceptually it's still possible. Essentially, you're trying to break categorical variables into groups. So, for example, you have a test that are A, B, C, D. Everyone who picks B is together. Everyone picks C is together. People who pick similar problems or make similar mistakes might be grouped together. So again, this is all about grouping. Like I said, we're going to focus mainly on this area, and specifically continuous supervised learning, linear regression. But whenever someone's talking to you about analytical technique, think about this and think about, where does it fit? What is the problem? Are you trying to predict something that's categorical, continuous? And is it supervised learning? Do you have truth? Or is it unsupervised? You don't have truth. And that's actually really going to, that's the first thing I always think about when someone tells me about a new algorithm. So this is what we're going to focus on for this session. So here we have another incredibly useful way of breaking down problems. And so we've deep dived right now into the top right corner, which is right here. So we've said, let's look at continuous supervised learning algorithm. This is one of the more common groups. That top right corner is probably that, and anything that's supervised is very commonly used. And so not all algorithms are the same, though they're all can be used in different ways. Two dimensions I like to think about are interpretability and accuracy. So accuracy is how well you can predict something. This means that it doesn't matter whether you know why it's working, you just know it is working. It's predicting things very, very well. A really common example of this is neural nets. Neural nets, which have become incredibly used widely in the past 5 years, to anything from self-driving cars to image recognition to voice recognition. These are incredibly accurate given enough data. You need a lot of data to train a neural net. However, they're not very interpretable. It's hard to look at a neural net and say, oh, that gives me some big business insights. Instead, what a neural net generally tells you is this is what the prediction is, but it doesn't necessarily give you much information about why. If you want to know why, you probably would go to somewhere over here to linear regression and decision tree. Linear regression gives you an exact relationship controlling for all other factors of that factor linearly. And that's really useful for making decisions, for understanding why something is happening. Decision tree also is quite useful. It allows you to break down what is the most important variable, what's the second most important variable, where do I make decisions. Humans often think in terms of decision trees. Now, these three, you may have heard them. You may have people talked about them. I'll just go over quickly what they mean. A k-nearest neighbors is an analytical technique which says, I am going to predict the value, which is the average of my k, or 5, k is a number, 3 nearest neighbors. So if I gave you someone who looked like me, and you said, okay, this person graduated from college, they work at McKinsey, They are from the US. They live in Boston. I would now predict my income, for example. You might not have someone who's exactly like me, but you might have someone who works in McKinsey, is from the US, who lives in New York, which is close enough, and that's a prediction. That's a k-nearest neighbor technique. Random forest is a combination of decision trees and is actually somewhat interpretable for variable selection, but not nearly as interpretable as linear regression decision tree. Support vector machines use a line which creates the most amount of variation, essentially splitting in a multidimensional vector, splitting two different groups, and then you take, if you do this for a continuous task, it takes the average, for example, of those groups. Anyways, so these are three, you'll hear them. Just know that they're less accurate than neural nets, they're less interpretable than linear regression. They are able to be used with a medium amount of data relatively easily. All of these don't need too much data to work. Neural nets need a lot of data to work. So I've given you some of the basics on these techniques. Now what I'm going to ask you to do is to pick a technique for different problems. Now, you may not, if you have a lot of background in statistical techniques, great. This should be very fast. If you don't have any, then you may need to do some outside research. So I'm going to give you guys, take 5 minutes if you need it, take 10 if you have no background, and do a little bit of searching around. What is a k-nearest neighbor? What is a random forest? What is a support vector machine? And figure out which analytical techniques you would use. So you're working for a retail company, and you have these 4 examples. You're trying to find factors which lead to sales. That's one. This is to classify images. On Instagram, you're supposed to segment customers. You're supposed to predict whether or not a customer will churn. Remember, this is actually coming from all of here, so some of these might be unsupervised learning. So think about it these ways. Is it supervised or not? Is it continuous or not? Then you'll find a quadrant. Then pick, how much data or how accurate does it need to be, and then you can pick one of these if it falls within there. So let me give you guys a few minutes for that, and then we will come back together and discuss. Great, so I hope you took some time to think about each of these. Let's go over them together. And if you haven't spent any time on it, you just skipped ahead, really take a minute. You are doing yourself a disservice. You're not helping yourself out. So really do help yourself out, be your best friend, and the only reason you're here is to learn. So take some time, pause this video, and look at it. Okay, the first one, finding factors which lead to store sales. So finding factors, we need that to be very interpretable, and it should be accurate. We don't want inaccurate answers, but it doesn't need to be it doesn't need to be perfect. It's more important that we have interpretable results than we have incredibly accurate results. So let's go back. So we're trying to predict store sales. So that falls into we're trying to predict something which we have data to. That is a supervised technique. We're also trying to predict sales. That's continuous, so we're in this quadrant. And we want it to be interpretable. So interpretable means that it's probably either a linear regression or a decision tree. So honestly, I would pick probably linear regression because it's one of the best. It's very actionable, but you could also pick decision trees. So that's one. Next, let's classify images on Instagram with your brand. So to make sure this is clear, this question is asking, try to go over all the pictures on Instagram and find all of the images that you have your brand. Imagine that you work for a soft drink company, and they're looking for all pictures with their soft drink so they can promote it. So you don't need this to be interpretable at all. You just want really good predictions, and you want it to be very, very accurate. So let's again go back over here. So you're trying to predict whether or not trying to predict something. That means that it is a supervised learning. You're trying to pick a category. So that is right here. So we're looking in a categorical prediction. Does it or does it not have my picture? And then it doesn't need to be interpretable, but it needs to be really accurate. So I'd probably pick a neural net for this. Anything to do with images also could tip you off that you should use neural nets. So you're now trying to segment customers into different groups. So going back here, we don't have any truth. So there's no predefined groups. So you're creating the groups. So it's unsupervised learning, and you are trying to likely you are using data which include how much they've purchased, etc., not just categorical. So that's probably going to be continuous. So you're going to use something right in here. The best clustering algorithm is probably one of the most common ones, k-means. So this would probably be a k-means equation. Finally, predicting whether or not a customer will churn. Again, let's go back final time. This is a prediction, so we're on this side. Churn is an A-B, it's categorical, so we'll be over here. So we're going to be in this quadrant right here. And in this case, you could choose a variety of different techniques. If you, frankly, this might be something I would use a random forest for if it doesn't need to be too interpretable. If I had a ton of data, I might consider a neural net, but neural nets are better for a little more unstructured data, like a image or text or sound, for example, or video. So I might use a random forest. You could consider using neural nets. You could even consider using linear regression. It depends on how much interpretability you really want at the end of the day. So that is these four. And so now we're going to dive into linear regression, which I'm really excited about. So let's talk about one of my favorite analytical techniques, and that's guessing. No, excuse me. That's not right. Let me tell you about one of my favorite analytical techniques, and that's linear regression. That's right. There we go. So linear regression, just go quickly back where linear regression fits. Linear regression is considered supervised continuous supervised method, meaning it's right here. Continuous meaning that you're predicting out a range of values. So that could be income, that could be number of people, that could be the number of stores which will be affected by a hurricane. Who knows? Anything that's continuous. And linear regression is a more interpretable method that doesn't require too much data. I mean, we'll actually be showing that in this example here. The income prestige data set that we've been using has about 150 data points, not that many. Something you could honestly not do with a neural net. It even might even be difficult to use a random forest or support vector machine with it. Though you probably could. Okay, so let's go linear regression. There's actually two types of linear regression which are important to distinguish, or types of linear regression. The regression technique, just to step back a little bit more broadly, is one of the most important techniques to understand when you're thinking about analytics. And that's for two main reasons. The first is historical. Regression has been around for 30, 40 years, and up until the early mid-2000s, most innovations in analytics were different ways to use regression, or a lot of the innovations were. So you would have, we won't talk about it here, but logistic regression is a way of doing regression for binary outcomes. There's an idea called generalized linear models, which are really forms of linear regression which use transformations, and those allow you to have graphs which are not straight but instead curved. They're transformations linear regression. So there's a lot in linear regression. Very effective technique, been used for a while now, actually 30, 40 years. And that means there are a lot of really good methods with it. So that's one. The second is And that's why actually for a lot of people, you will hear about it a lot and it'll be used in a lot of problems because it has such a historical legacy, so people understand how it works. The second is that linear regression is one of the most statistically rigorous methods, and it's really based in different distributions. In linear regression, it's based upon the normal distribution. It assumes normal distribution of errors when you're predicting. And so when we try to interpret the values, if you have enough understanding of statistics, which like we discussed in our live, is really a base layer that you need to know to be an effective analyst, then you can make a lot of interesting claims about what you're seeing in the data. So that's the reason why that linear regression is so widespread and so useful. But within linear regression itself, there are two types. So the first type which we're going to explore first is a single variable regression. This is having two variables, for example. In this case, we had education, number of years of education, income. That's a straight line prediction. This is the simple linear regression. A multivariate or multiple linear regression involves multiple different variables of prediction. So an example might be education, percentage of gender, age, and the way that it actually is doing the regression is in one dimension. Just to show this, in one dimension you are seeing a relationship between a y and an x. So a simple linear regression is just measuring this relationship between these two variables. If you have three or more variables, let's imagine three variables because we can imagine it in our own minds. You would have these two lines, but then you'd also have a third axis right here, which would create a three-dimensional object. And we'll show this in the example. And the regression line now actually sits in 3 dimensions. And so it's still a straight line, but it's passing in 3 dimensions. If you had a fourth dimension, which we can't imagine, but you could think of it as time, then I can't do it because we live in 3 dimensions. Fourth dimension, then it's a straight line. And so it's controlling for each of these factors. When you have a multiple linear regression, what you're saying is, what is the effect of, for example, education on income, controlling for these other variables? So that's the difference between the two. Simple linear regression is one variable, multiple linear regression is multiple variables, and you have this added complexity, this added benefit that you can control for other variables variation. So this is probably a good time to say, we understand that there is a variety of backgrounds in this class. I think it's useful to review. I have probably studied linear regression in every single data science course I've ever taken because it's so fundamental. So I may have done it 6, 7 times. I've taken classes on linear regression. I once took a class exclusively on linear regression. So if you feel that you understand it so well that you don't need to go through it, that's fine. You can skip ahead in the video. But if you want to review, which I would recommend, then just follow with us. And for those who are new, if you want more detail, more rigor, we should talk about that in the live, and I would also talk to your TA about it, and we can get even more statistical, get down deeper. But this is a linear regression for now. We just need to review this in order to get into the business question. So here's some examples of a linear straight line. So this is 线性, right? 线性 is like straight line. This is a perfectly correlated graph, negatively correlated, positively correlated. This is somewhat correlated. You see with errors somewhat we call normally distributed across here. Here is another, again we see the linear line which seems somewhat affected, but you even have more errors, meaning it is even less related. And then here again we have there's no relationship between y and x, or in this case you would also say there's no relationship between y and x, because it seems like it's all the same value of y for all values of x. So when we're saying a linear line, seeing right, we're referring to this straight line. So that's what we'll be referring to. So linear does not necessarily mean that, something is not linear. It doesn't mean that there's not a relationship. And here's a case in point of this. For our two examples on the left-hand side, we have linear relationships. It's very clear. It's a straight line up, it's a straight line down. This is probably a little bit more correlated than this. But to the human eye, if we look at these two, we would say, oh, there's definitely a relationship. It kind of looks like an upside down U, or it looks like it's going and speeding up. It's exponential. So you might have, and this is what we saw before, you might have no relationship if you're just doing a linear line. So the linear line here might be right here. But that doesn't mean there's not a relationship. So when you are doing linear regressions, investigate the variables and figure out, well, does a linear line actually make sense here? And we'll be doing some of that. Does it make sense? Here again, there's definitely a relationship, but it's not clear if it should be a linear relationship or not. Again, here we have strong relationship, very tightly correlated, and a weak relationship. So we have a lot of variables. But regardless of whether it's strong or weak, you assume within a linear regression that the variation or the error is normally distributed. So most of the error should be around here, some of it will be around here. And a normal distribution is it looks like a bell, like that. This is a strong relationship, this is a weak relationship. And then similarly, here is no relationship. Even if it's spread out or tight, we would say there's no relationship between these two. So again, that's so let's look at a simple linear regression. And we don't need to go into too many details because if you guys really want to dive into the mathematics behind it, it's really beautiful and fascinating, and I would suggest it. But this focus of this course is to bring everyone onto the same level, so they're speaking the same language. We're not going to go into too much detail, but it is important to know the equation that is being used. So there are 5 main parts to it, as you can see here. This is called beta. Beta 0 refers to the beginning or the start of the line, assuming that x is 0. So it's really just a shift. So this is, for example, let's say this is 1. This might be 2, or it might be. This is what it's referring to, this spot right here. If we didn't have beta 0, all lines would start from 0, 0 point. And so you would get some weird effects. So this is changing the start of the line, shifting up or down. Beta 1 refers to the slope of the line, how sloped it is. This is probably slightly more sloped than this is. This is negative slope. This is positive. X refers to where in the x-axis it is, so right here. If it's farther along, then we would go farther down the line. And this error term right here refers to how much error the line is. So in this case, you would predict a line by just looking at beta 0. We start right here, we go up 2 because of x times this beta 1, and then the error describes how much variance or how much what the residuals are around that line. We will focus on, when you're doing a linear regression is using a technique to predict what beta 0 and beta 1 are, and they give you these lines. This is not a linear relationship. So that's what we'll be looking to create. So here's an example of a linear regression in our previous data set, and we'll actually dive into this. I'll give you guys a little example in a second in my data set. So here is the relationship between income and education using a linear regression line. You can see, so let's spend a quick second to say, does this make sense? So think for yourself, does this seem like a good line? You don't need to know anything about statistics to look at a line and say, does that seem like it's matching the black data points I see? So let's look at it. So it seems like it's doing relatively well. This seems, especially this area seems to be doing okay. But if I were looking at this, I might say, well, it looks like this. It might look like a little bit of like a curve up like that. So is this the right form? Again, you want to have this error term right here. The error term is assumed to be normally distributed, so you would expect the error to look like this across. But what we're actually seeing likely is we're under predicting here, we're over predicting here, and then we're under predicting here. So something's a little strange about that. Maybe we're predicting right over here, but we're definitely under, and then we're definitely under predicting right over here. So this is this is an example, and this is actually a really good thing for you to do when you create a linear regression, is to just spot check it, especially if it's a simple linear regression like this with one variable. Spot check it and say, hey, does this make sense? And if it does, great. If it doesn't, you may need to change your variables. You need to update your variables. Now, the question is, how do I know how good this linear regression line is? And one way, a intuitive way to think about it would be, how off am I from my predictions? So am I close? Is this line really close to these predictions? It was really close for this one, but it was kind of far away for this one, and it was really far away for these two. So these, if I was only looking at these, I would say that's a terrible prediction. But if looking at this, I would say it's a great prediction. So the way we intuitively measure error is by adding up the errors right here, how much your errors. It's actually the squared errors for a few mathematical reasons. And then dividing that by a comparison to the average. Like, what if I just predicted the mean? So that is what we call R squared. R squared is a measure of the success of a line, how effective the line is at predicting. What you really need to know at a high level is that I would say, two main things tactically. One is that R squared goes between 0 and 1. So R squared of 1 would mean it's a perfect fit. It matches every line. You should almost never get an R squared of 1. If you're getting an R squared of 1, there might be something strange with your data. You might have more predictors than data points. So you shouldn't have an R squared of 1. R squared of 0 is possible. It means that your predictors don't at all predict income. So for example, I could have, for income, if I had one of my variables was number of times employees go to the bathroom. My guess is, I don't know, maybe if you go to the bathroom a lot, you're less productive. But my intuition is that bathroom time is not related at all to how much income you make. I dearly hope so, because I go to the bathroom a lot. So that would come out as an R squared of 0. But if we're using education, if we're using prestige, gender, you might assume that you'd have some relationships you expect between 0 and 1. So that's one. Tactically, it's between R squared is between 0 and 1. The second thing to know is that R squared is a comparison. R squared is, you're looking at the difference, you're looking at how much variance, what's the distance between points and lines compared to the distance of the point and what the line would be from the mean. So this is just y. This is just the average of the value y. This would be a very simplistic prediction. I'd say, okay, for all of my values, I'm just going to assume that the prediction is the mean of the predicted value. So I would say for all of these professions, I'm not going to look at any other variable. I'm just going to say the average income is the income for all of that's going to be my prediction. That would obviously be not a great prediction. It would create a lot of errors. So that's our baseline. And then how much better compared to that baseline is essentially what we see with the R squared. So that's really what we're looking at when we look at R squared at a high level. Of course, there are other parts to it, but it is simply SS reg. R squared is SS reg right here divided by SS total. So how much are you? What's the original error versus what is the new error? And that's how you find out the R squared. So essentially, it's between 0 and 1. 1's better, and it's a comparison of this very naive prediction. So how much variation did our model capture? So yeah, that's right. How much variation did our model capture? Our model captured 0.33. In practice, it's hard to say what is good or bad, but it's actually not bad. Oftentimes on a project, you'll make a prediction, you'll only capture 15% of the variance, and that might be not bad. It's still useful, but it's not a lot. 0.33 is pretty good. It's not great. I mean, something like 0.6, 0.7 is when you get to a really good model, 0.8. But 0.33 is not bad. So and you can kind of tell that right here. So this is, a pretty good prediction of what we're seeing. It might be better if you had a little bit of curve relationship, but it's not bad. So R squared of 0.33 is pretty good. So let's go through an example of single variable. Let's go through an example of single variable regression in R, and then I will come back and we'll go through multiple linear regression and then do another example in R. Great, so let's go through the Prestige example using R. And R is a really great tool when you're doing statistical analyses. R was really created for statisticians, and it was created for people who wanted to use packages that are easy to understand and which are very easy to interpret. So let's go through that. I'm bringing in some libraries. And let's, again, whenever you're starting analysis again, always re-inspect your data. Just make sure it's what you expect it to be. Is this what it looks like? So we looked at this last time. Education, number of years of education. Income is in Canadian dollars in 1970. Is it 1 or 2? 1971, 1972. Prestige is the prestige out of 100. Is it prestigious? Education. So we'll look at that. So we're just going to choose one. I think we're going to choose education relationship. Look at the data set here. We can also look through chemists, high education, okay income, some women, not very many, and high prestige. So this is just an example. Okay. So let's, again, this is another way. STR is another useful function which looks at the first few variables, makes it a little easier for you to see. Tells you what type of variable it is. This is numeric, this is integer, this is a character, or sometimes referred to as a string. And then summary is a good one as well, which I like. Here we go. So we got education is a type character, so you can't find the minimum or max. But here we go. Education minimum 6 years, max 15 years. So creating a new data set just to take the second and third variable, that will be education income. Make it easy enough for the prediction. Here we go. Here the education income are the only two variables we're looking at. And let's take a quick look again at education. Relatively normally distributed. The variable itself doesn't need to be normally distributed in order for you to use linear regression. That's a little bit of a misunderstanding. The error, though, needs to be, or is assumed to be. But it is often easier if a variable is normally distributed for you to make that prediction. So oftentimes you'll see transformations. Like right here, income is like income in general, amount of money is often right-tailed, meaning there's some really rich people out there, maybe you, I'm watching you, and then most of us are just right here. And so oftentimes people will what's called log transform to make this a little bit more normal, but you don't need to. Here we go. So here is the relationship between education and income and education. So each point in the line, each point represents a profession. So again, observe how we're growing over time. And then again, this is the linear regression equation that we discussed. So this is what we'll be using. Let's see. What we're going to do is we are going to center education at $6,800. That's right around the norm, so that for every increase in so that's essentially just going to give us an average. What does the average person's income look like? Otherwise, you would start at some kind of meaningless intercept, which would be somewhere around here. You could even have a negative income, and that wouldn't make sense. So we're just going to start at the average income, or excuse me, the average education, which is probably right around here. Okay, that's why we're centering it. You don't need to do it. Actually, won't change the outcome. But here we're just saying 0 years of education refers to more than, I think it's 11. Education.c. Yeah, we can actually figure that out. Mean new data. Education. I'm not sure if it's the mean or the median. It might be the mean. So 10. Yeah, so around 11. It's around 11. So and here LM. So LM is the package, or is a it's used a package in R to do linear regression. This is one of the easiest ones you'll find. So I just did it. I'm regressing. I'm predicting income, which goes before the squiggly line, and then I'm using education, centered education, and the data is new data. And then you just do a summary of that object that comes out. Go. Here we go. And then this is really what you're looking for. This says that 3 stars is very significant. 3 stars means it's under. The p-value being less than 0.05 is a rule of thumb, meaning that a variable is significantly related. And so here we have education. For every year of education, you increase your yearly income by about $1,000 or $900. For an average amount of education, you're expected to get around $7,000. So if you think you studied for 11 years, in this case, that means probably graduating high school, you would expect $7,000 a year. If you studied more, you could expect about $1,000 more for every additional year of education. A useful line. And this is the how. And then, okay, let's look at the R squared as well. Here's a multiple R squared. 0.336. Adjusted R squared refers to another way of measuring R squared, but it takes into account if you have a lot of variables, it will penalize you, because if you have a lot of variables, you can create statistically irrelevant relationships, but relationships that a linear regression will pick up on, will believe to be relationships which are not, and so it will make your R squared seem higher than it is. So adjusted R squared puts a penalty on having too many variables, which is good. So you can look at either of these. Right now we only have one variable, so 0.33 is about the same. And then we just look at what we looked at before, which is the shown below. Intercept. That's great. And then this is, so now we've looked at the model. It says that we have a good R squared, not great. Let's look at the residuals. Remember, this is supposed to be normally distributed, and again we see not quite normally. You're seeing, down here we have a lot of values that go down here, which seems not quite normal. It might indicate some pattern that we're not capturing. There's a box plot. So here we go. And this is Box-Cox transform the optimal lambda value. This is a potential way to rerun this rerun. Yeah, exactly right. Rerun this. So we're essentially saying, hey, I actually don't think this relationship is straight. I think it is curved in some way. What box plot lambda does is it creates essentially a curve function. So it curves it creates a power. It curves the line based upon the power of lambda. This is you can look this up if you want to get into the technical details, but essentially it's creating a curved line, and we'll transform our variables with this optimal lambda. You can see we are taking it to the power of this optimal lambda, calling it income transformed. The transform data looks maybe a little bit more normal, less right skewed. Maybe this will produce a better result. Yeah, here we go. Again, it looks a little bit more normal. This is transformed income here using our transformed statistic. Let's see. Here we go. Yeah. Let's see if this actually makes a better model. So model 2, we're now predicting the transformed income, and then let's see how well it does. And it looks like it is pretty much identical to what we had before. So in this case, transforming the variable, which you can try in your homework and I would try with your project, is a way of creating better variables, but in this case it didn't help. And that's often what you'll find. You'll try to transform things and they won't help. So this is just a little bit of a view of that. Yeah, transform income is normal. And the plot, again, you see a pretty similar line before. And you know, like we wrote it here, the Box-Cox had almost an unnoticeable improvement in the model. And because we're usually looking for more interpretable models, we won't make the transformation. So this does not seem like a good model, but perhaps we need to bring in other variables, right? Maybe it's not just income, which predicts, or excuse me, education that just predicts income. And so that's what we're going to look at in the next session with multiple linear regression. So let's jump back to that. So here we are. Again, we're going to look at multiple linear regression. So what if you wanted to include something besides just education to predict it? For example, we wanted to predict income, but with not only education, but also prestige. Then we would create a model that looks like this. This is very similar to what we had before, and essentially goes like this. Y hat is the predicted value, in this case income. A is the intercept. Beta 1 is the first coefficient of x1. In this case, x1 you could call education. Beta 2 is the next coefficient of x2. x2 might be prestige, for example. And then you could add in an error term like we saw before. So I'm showing you guys different formulations of this, but it's very similar. In this case, we called it beta 0. In this case, we call it A. It's the same thing. It's just a slope intercept. In this one, we don't include explicitly the error term, but it is also there. We assume that there is some error there. Again, we're basing the standard regression off of residuals. We're trying to minimize the residuals, so minimize the amount of error that we have. This is actually very similar. We're just taking this single level concept and expanding it into multiple dimensions, and that's essentially what is happening right now. This is a look at the a three-dimensional-ish look at what a prediction is doing. And here we are predicting, because it's in 3 dimensions, we're actually predicting on a plane, not just a line. You're always predicting a level below the number of variables that there are. So you're making a prediction on the plane of this 3-dimensional object or 3-dimensional space. And you have a response plane, and this is essentially trying to minimize the errors in 3 dimensions, as you can see here. So we're trying to minimize these errors, but not in 2 dimensions now. Now we're in 3 dimensions. So we have an intercept alpha, where it starts when all of the values are 0. We have x1, which predicts the slope of beta 1, which refers to the changing slope for x1. x1 we could call education again. Beta 2 is the same, but beta 2 might refer to another variable. It would refer to another variable. In this case, maybe it's prestige. So we've done the same thing as we had before. The main difference is that when you're looking at the coefficient, so last time we said, okay, you have an increase in education by 1 year that relates to $1,000 or $900 worth of more income, or predicts $900 more income. In this case, there's an added layer. It's not just that, it is that, but it says we're adding $1,000 for every year of education, controlling for all other variables being the same or being constant. So controlling for prestige being identical. And that's really the power of linear regression, is that you are saying, controlling for other variables, saying, let's ignore them. What is the effect of this single variable? And that's useful because when we're looking at variables are correlated. So for example, prestige and education are very strongly correlated right here. As you can see, and this is the same thing. That means that the effect of education or effect of prestige might actually be an education effect. So just because you have a cool job doesn't mean you might make more money. It might be because if you have a cool job, prestigious job, you actually got more education. So one of these factors might be the explaining or the explanatory factor, and the other is not. So just to repeat that, when we have multiple variables, they might relate to one another. And so in using linear regression, we can distinguish the effects of the variables that are related to one another. So we can say, oh, controlling for prestige, education has little effect, or control for education, prestige, little effect. So let's do this in R. Let me show you what it looks like in R. So now we've got multiple linear regression. Let's just re-upload these libraries. Similar before, again, we're going to be, in this case, I'm going to make this as simple as possible. I'm just going to use 3 dimensions, so 2 predictor variables, 1 predicted variable, response variable, income. I'm going to use 3, education, women, and prestige to predict income. So you don't need to subset the data set, but I am here. Just make it a little bit cleaner. So here we go. Let's plot this. This is going to show us the relationship between these 4 variables. Again, we have correlation here. Looks like women and income are negatively correlated. So more women, less income. Women education doesn't seem to be very related, actually, at this point. So maybe at this point in time, women are as educated, yeah, it's possible at this point there's no relationship between percentage of women in a profession and the amount of education. So let's go back to our exploratory insights, and we're trying to validate them. We had 3 main insights. One is that education is positively related to income. So that's what we saw here. Here. The next is that prestige is positively related to income. So that's right here. Again, we see it. Yep. The more prestige, the more income you have. And the third is that the percent of women is negatively related. So let's find out that if you can, whether or not this is true using linear regression. And the added nuance, the added twist here is that we can control for other variables. We can control for education when we look at prestige. We can control for women when we look at education. So this is the model that we're doing. Beta 0 plus beta 1 times education, beta 2 times prestige, beta 3 times women. Again, we're centering predictors, so the mean is at 0. That's great. Excuse me. So we've got our new variables, we've got our new centered variables around their mean. And let's build a multiple linear regression. You can use the exact same syntax. Income predicted by these three variables, just do a plus sign and then the same data set. So let's do that. And here we find something interesting. So we find that prestige is positively related with income. So every additional point of prestige, you get $150 more. And women is negatively related. For every added percent of women in the profession, you earn $50 less. So maybe a sign of discrimination. This is a much better model. It's a 0.64. So this is capturing about twice the amount of variation than we had before. So that's really good. Now, something weird happened here. We had education as being one of the most important predictors, taking 30% of the variation previously. And now when we added in prestige, we have a result that says that education doesn't matter at all. So that seems weird, right? Even in our intuition, we might say, well, it still seems like education should matter. But it looks like education and prestige hold the same effect, meaning they are doing the exact same thing. So your linear regression will somewhat randomly pick which of the two of these should be significant if they're so correlated. And we actually get to choose whether or not we want prestige to be in the data set or education in the data. If we saw education was previously important, but now prestige is important, we can actually get rid of prestige and see what happens to our model if we want that to be. The problem with collinearity, collinear mean they're both correlated, is that you will get some predictors which are insignificant because you have two variables, one masking the effect of the other. So let's try again, and we can see how they're correlated here. So look, prestige and education very highly correlated, meaning that if you add these two, one will cover the effects of the other. So I'm going to actually use education, and I'm going to use education in this model because education is more actionable than prestige. I don't really know how to make my job more prestigious, except by telling you how awesome it is, but I know I can get more education if I need to. I can go back to school. So let's just create that model now. Unfortunately, this means our model's worse. So that's weird. So we have an R-squared that's 0.56. Previously, we had it as 0.64. So you're losing a lot of your predictive power. So we have to think about this. Do we want to use, and let's actually go back here. Let's actually try it for prestige. Yep, we have a 0.64. So we have a choice right here, and this is actually a really common choice that you guys will have to face, is do I want a model that is slightly more interpretable or actionable with education, or do I want a model that is more predictively accurate, in which case I would add prestige. So even though linear regression is one of the most interpretable, we still have to make that choice. And so in this case, I might even choose the worst model in terms of accuracy, because I think that education is more actionable. I can do more with it. But you might choose something opposite. Here we go. We're seeing the residuals and fitted. And again, we have some outliers here. So we're not quite predicting. We're under predicting here. We're over predicting here. This indicates we might want to transform our variables. And that means that we might want to make them. Okay, so this is showing a 3D model. Kind of an awesome visualization, 3D model. Again, you can kind of see this is women, this is prestige, this is income. You can kind of see a curve right here, three-dimensional curve. So let's try to model income, but let's log income and let's take prestige squared is what women squared. This means that you now can have a curvilinear relationship. Let's see if this improves the model. And actually looks like it improves the model quite a bit. So when you're doing your upcoming task, think about transforming variables. And this will allow you to potentially make better predictions. But when you transform variables, it gets a little bit harder to interpret. In this case, what this means is that if you increase prestige by 1 point, it has not only a linear effect, but also a multiplicative effect, meaning that the more prestigious it is, it will over time curve down, so it won't go as fast. So it's initially more fast, and then it will slow down over time. We can get rid of, again, here's where this is the transformation of income. Again, you can see more of a straight line, which is what we want. Women's squared was not significant, was not below 0.05, so let's get rid of it. And let's see how that makes our model change. Yeah, so here we have a very similar model. It actually looks like it's about the same, a little bit worse perhaps. So this is again a choice for you guys, whether or not you want to use this model or not. So essentially what we found out is that in our best model, what relates to income is prestige and the percentage of women in the workforce, and it might be a curved relationship. So the more prestigious you get, you have diminishing returns to prestige. So at first it's really effective. The more prestige you add, you gain a lot more in terms of income, but then over time it tends to diminish with time. So I just want to give you guys a little bit of the R of that, and then so you guys can use this in your own. And you feel free to use some of this code to make it a little bit easier for yourself. So now that we've gone through linear regression, how do we explain an analytical technique? And I think there's a really good analogy here for if you're a more technical person explaining something to a less technical person. And I'm going to give you the car mechanic analogy. So I don't know if you guys own a car. In the US, it's a rite of passage that when you're 16, you have to start driving. So a lot of people have a lot of experience with cars. But if you don't own a car, I'm sure you can imagine this. What happens when your car breaks down? So let's say your car breaks down and you need to go to a mechanic. And so you're trying to figure out, you're going to the mechanic and you talk to them and you say, doc, or mechanic, my car broke. I don't know what's happened. I think the front wheel is weird. What should I do? And so let me give you two examples of what the mechanic could say. In example one, the mechanic might say, okay, I'm looking at your car. It looks like you've got a lug wheel right here on the fourth tricep. I'm going to remove that, re-oil this, fill it in, use a triple bi-tart lock to make sure that it connects together, and then I'm going to re-engineer the wheel such that it fits perfectly, and then he keeps going for 5, 10, 15 minutes, and then finally, you're going to need to not drive for the next 2 days. So that's one. They give you option one. They give you every single detail of what they're doing. Option two is, mechanic says, okay, we're going to look at it. I'm going to need to fix up this wheel. It's going to take me 2-3 days, say 3 days. I'm going to need $400 to fix it, and I'm going to need you to not drive on it for the next few weeks. The wheel is popped out, and we'll need to replace it and put it back in. So in that second example, they started with the conclusions. They started with what you need to do and the action steps, but only then did they go to the results and why exactly that is. And so when you're talking about an analytical method, think about yourself as a car mechanic. You don't want a car mechanic that's going to tell you every detail. And if you're a manager, you don't want to hear every detail. If you own the car, you don't want to hear every detail of how the mechanic is going to fix it. You just want the mechanic to fix it. And if you're a manager working with data scientists, data analysts, you don't want to hear every single detail about how you clean the data or how you adjusted a variable. You just want to know what's the results and what are the implications for me. So when you're thinking about presenting something, think about that, an analytical information. Think about how can you make this as easy to understand as possible for the other person? And how can I focus on what really matters, drawing out the main insights for them without any of the technical, any of the technical words or phrases that you would normally talk to. Two mechanics talking to each other is very different than a mechanic talking to a customer. So I'm going to run you guys through an example, and then I'm going to let you guys work on this. So how do we make this something that is more understandable? This is exactly what we saw in the R code. For you, it might make sense. Essentially, it says, well, we're looking at income, we're using education, women, and census, and type to predict it. The two variables which are significant are education and women. Education is positive related, women is negatively related. The other three don't matter. And you've got a decent R squared, 0.57, so it's a good model. But imagine if you've never seen this before. This would just look like a bunch of words. You would have no idea what to look at. You would look at this block of text. It'd be really confusing. What does this mean? Should I be looking at the word freedom? Should I be looking at the p-value? What am I even looking at? So that is this is like what not to do. And I've seen this so many times that data analysts make this mistake. They will just print out the results from their Python or R, and they will give it directly to their manager or their team and say, here's the results, without giving any explanation for what it means. This is the mechanic saying, let me give you all the details of what I need, but I'm not telling you what you should be looking at, why you should care, or what you need to do. So this is not what to do. Let me give you a better example. So this still uses a pretty ugly graphic in the center, but it's better because it allows you to see, it points out some of the main takeaways. So this is the equation we used. Controlling for other variables, it says, looks like type of profession is unrelated, gives some big insights. And then here we go. For every 1 year increase in education, we see an increase in $800 of yearly income. 800, there should be 800. This is calling out insights. So this is a little bit better. It's making it clear, but still I don't really know. There's some things that's missing. It's not very visual. It does not describe where the data is coming from. It does not tell me what are the main things I should get away from this. So it's better, definitely better, and this is better than what this would be. It's pretty bad. This is much better, but you could do better. So I'm going to give you guys 3 minutes, or let's give you guys 3 to 5 minutes to sketch out. Either you can write it down or you can use PowerPoint and make it. What would be an even better page? And think about the mechanic analogy. Three things. What do they want to know? What are the takeaways for them? And what do they need to do next? What are the next steps for them? So I'll give you 3 minutes to work on that. So what did you come up with? There are plenty of different answers for what you could do, but I'm going to give you a quick example of what I would have done. And you can even use this page when you're creating your explanations for your homework. And that is, here's what I did. So I removed all of the numbers from it because I decided it didn't really matter what these specific numbers were. I just wanted them to know direction. So it's a visual table created and called subscribed on the site. And essentially this is saying, what is the relationship between profession and the income characteristics? Immediately, it's very easy to see. I look first at this. So, okay, education, positive related. I get that. Gender, negative related. Okay, I get that. Looks like the census data doesn't matter. Work, profession, doesn't matter. Potential insights. So if you want more income, then you should actions or takeaway actions. If you want more income, you should study more. If you want to make more money for women or men, select a profession with more money. This, of course, in the 70s. And then what are my insights or takeaways? So to get a higher paying job, you want to keep on studying, and similar again. If you want a job jobs that have higher income generally have fewer women. So this is an example of a very visual slide that says does not even use any numbers, but gets across a really easy and simple to understand message. And you can see why this would be easier to understand to someone than this, and much easier than this. So think back to the car mechanic analogy. When you're presenting analytical information, you are going to be, you want to explain why do they care, what is happening, what do they need to do, and you don't need to dive too much into the details like I showed here. If you're speaking to a mechanic, you want to be very specific about what the problem is and what you want out of it. My front tire is broken. I'd like it fixed in 3 days. Can you do that? So the opposite's true, but you don't, again, need to go into too much of the details. You need to speak of what is important, think of what is important, and share it. So that is it for today. Look back over the learning checklist and say, did I understand everything that we talked about today? And if not, go back to the section and try to figure out what was it that you didn't understand. Bring questions. Look through, and I'm going to ask each of you guys, think of at least one question that you feel you need to figure out, and bring that to life this upcoming week. And we'll talk about it. Go through this quickly. And then for the video game performance, we already went over this, but here is the project for today. You're going to be creating a multiple linear regression like we talked about. You're going to be filling out the data sheet, figure out which data you want or don't want to clean. And then you're going to develop a quick 3-page PowerPoint deck, as we would call it in McKinsey, of your insights, and you're going to send those back out. And then you're going to also finish these additional readings that we have. So that is it for today. We've got some really cool readings. This is the worksheet I showed you before. Check out these additional readings. They're really some interesting ones. I think you'll enjoy them. And I look forward to chatting with you guys really soon. If you guys can get down data cleaning and picking the right analytical methods and presenting that out well, then you are so close to being one of the best analysts out there. Tomorrow or next session, we're going to figure out that what's that final step, and that is communicating powerfully and effectively your ideas so that people are inspired to take action because of your analytics. So that's it for now, and I will see you guys soon.